So this lecture is about a concept that's related to topological space or a subset of topological space, or if you want a metric space, being somehow connected, right? So we're going to be talking about connectedness over the next few videos. There are actually two competing conceptions of what it would mean for a space or a set to be connected. And we're going to start with a concept called pathwise connectedness. And what it really means is extremely simple. So let me give you, you have a topological space, and you say that 2 points in a set inside the space U are connected by a path inside U. We're going to use the symbol, right? This double arrow going from A to B with a U on top. So we say this when there is a continuous curve mapping 0, 1 to U, right? So it's a continuous curve, right? So if this is the set U, you're asking that this continuous curve lies completely inside U, and that it connects gamma of 0, which is A, to gamma of 1, which is B. So this is what I'm asking. Of course, calling this gamma is not completely correct, right? Gamma is the function that maps 0, 1 to this path. But I hope that the intuition is clear. We're just saying that we have a connection between A and B through a path that lies entirely within U. And by definition, U is said to be pathwise connected if any 2 points inside U can be connected by a path like this. So this is sort of geometrical, easy to understand. Let us notice some properties that are going to be important. So I'm not assuming right now that U is pathwise connected. What I want to do is prove properties of this relation, right? So, and so let me call this proposition. 1 is that for all A in U, A is connected to A itself. 2 is that for all A and B in U, A is connected to B by a path in U, if and only if you have the same thing in the opposite direction. And 3, if A is connected to B, which is connected to C, this implies that A is connected to C. Okay, let's check this. Hopefully item 1 is clear. It's basically saying, okay, if you have a curve from A to B and you take the, item 1 is saying that A is connected to A. How do you prove that? You take gamma defined to be constant and equal to A, right? So gamma of T is equal to A for all T in 0, 1. So that's surely a continuous function because it's constant. Oh, by the way, right? So we're talking about topological spaces. So I need to show that the pre-image of open sets is open this interval. I mean, we have a definition of continuity for topological spaces, right? But and okay, here we have a topology, and here we have a metric. Well, topology given by the usual metric over 0. Okay, but it's easy to see that this is continuous. Okay, so the second step is showing that you can reverse the curve, right? So that you can go from A to B via a curve, you can take it the opposite direction. So if gamma continuous connects A to B in that sense, then this new curve, which I'm going to define here, gamma tilde from 0, 1 to U, that maps T to gamma of 1 minus T, right? So that's sort of reversing time. So this connects B to A and vice versa, right? So how do we know that this new curve, this new function I created here is continuous? Well, it's a composition of 2 things, right? First one is the map that takes T in the interval 0, 1 and replaces it with 1 minus T. And that's a continuous function from the unit interval to itself. And then I compose that function with gamma. and the composition of continuous things, right? So gamma is continuous. So the composition of continuous things is continuous. That's true in any topological space because you can look at pre-images and stuff. But if you want, you can just stick with metric spaces. In any case, because the composition of continuous things is continuous, so we're done. That this is going to be continuous as well. Okay, so that's items 1 and 2. Item 3 is only slightly more difficult. We need to show that if there is a path from A to B, and there's another path from B to C, let me call this path, I don't know, okay, call this one gamma 0, and gamma 1. So if you have paths from A to B and from B to C, you have a continuous path from A to C. And that's visually clear, so right, we just need to turn that into a rigorous argument. So let me erase this. But the interesting thing is that I'm going to give, we're going to try to give a topological proof that the kind of the joining of these two curves is continuous. Well, we're going to give a topological proof. In the sense that we're not going to use sequences to prove that it's continuous, we're just going to use topology, right? Okay, so how do we do this? Let's say that you have these curves, and I'm just going to say, well, gamma 0 connects A to B in the sense, right? So gamma 0 is continuous, gamma 0 of 0 is A, gamma 0 of 1 is B, and the same with gamma 1. Okay. Right, that's what it means to say that A connected to B, which is connected to C. Continuous with gamma 0 of 0 is A. Gamma 0 of 1 is the same thing as gamma 1 of 0, which is B. And gamma 1 of 1 is C. Okay, now if you need to write down a formula for a curve, right? So what do you need? A curve that maps 0, 1 to U, and which traverses the path of gamma 0 and the path of gamma 1. So that's sort of easy. Basically what we're going to do, because we want to have time, so to speak, between 0 and 1, we're going to traverse first curve gamma 0 at twice the speed, so we do that from time 0 to time a half, and then this curve at twice the speed as well. So here's how we define the gamma that's going to connect connect A to C. So this maps T to gamma 0 of 2T if T is less than or equal to a half, or to gamma 1 of 2T minus 1 if T is greater than a half. Actually, I mean, if you have greater than or equal to here, it doesn't make a difference, right? In principle, you have two choices, right? When T is equal to a half. But when T is equal to a half, here you have gamma 0 of 1. Here you have gamma 1 of 0. And the two are equal to B. So it doesn't matter which item you pick, right? Okay, so why is this continuous? Well, that's what we have to prove, right? But first of all, notice that if you restrict gamma to the interval 0, a half, this is clearly continuous, right? This is just gamma 0 composed with the function that multiplies T by 2. So with the composition of continuous function, it's continuous, right? Again, if I look at gamma restricted to 0, a half, it's continuous. If I look, because it's basically gamma 0. If I look at gamma restricted to the interval a half to 1, it's also continuous, right? Because this is continuous, this is continuous. So there's no doubt about the continuity in the two sides of the interval. Let me actually draw the interval 0, 1 here with a point a half in the middle. Sorry. So this interval is being mapped to something in U, right? So this whole thing here is mapped to this curve. Forget about the one on top. You have A, C, and you have B in the middle. And I argue, okay, the function restricted to this gamma, the function restricted to here is continuous, the function restricted to here is continuous. How do you show that the whole thing is continuous? Okay, so I'm going to give you a sketch. Well, it's actually a formal argument, but I'm just going to do it in the picture instead of writing everything down formally. Okay, so at the level of topological spaces, the only way we have to prove that something is continuous is to show that the pre-image of open sets here are open sets here, or, which turns out to be more convenient, the pre-image of a closed set here, F, is a closed set here. Well, something, I don't know, it could be funny shaped, but something. And here's how you prove this, right? So suppose you have a closed set here, and you look at its pre-image under gamma, right? So this pre-image is made of two parts. And that's kind of, okay, here I have a function that's not quite gamma 0, right? So this is gamma 0 tilde of t, and this is a gamma 1 tilde of t, but we know they're both continuous. So what you have to realize really is this, so that the pre-image of f under gamma is a union of pre-images. It's like you're saying, okay, I have f, and I have the curve from 0 to a half, and the curve from a half to 1. Each one of those parts gives me one part of the pre-image, right? Okay, so watch, right? So gamma, this first set, gamma 0 minus 1, gamma 0 tilde minus 1 of f, is like this part here. We know it's a closed set of the interval from 0 to 1/2, including 1/2, right? Why is that? Because gamma 0 tilde is a continuous function from this closed interval to u. So the pre-image of a closed set is closed. The same holds for gamma 1 tilde minus 1 of f. Why? We have a continuous function from 1/2 1, which is this one, and the pre-image of a closed set must be closed. So I have a closed subset of 0 1/2. I have a closed subset of 1/2 1. Now I'm saying, okay, this is a closed subset of this subinterval, right? 0 1/2. How do I know that it's a closed subset of 0 1, the full thing? Now we use this fact that we learned that since this guy is a closed subset of a closed subset, it's also closed to the larger space, right? It's about relative topology. All I'm saying is that, okay, gamma 0 minus 1 tilde of f is a closed subset in the relative topology of a closed subset of 0 1. Therefore, it's a closed subset of 0. This guy is a closed subset of 0 1 as well. And the same for this one. It's a closed subset in the relative topology of a closed subset. So it's a closed subset of 0 1, right? This guy here. And now what I have is a union, right? So gamma minus 1 of f is a union of two closed subsets of 0 1. And we know that when you take a union of two closed sets, or any finite number of closed sets, that's also closed. And therefore, this has to be a continuous function, right? So for any f, gamma minus 1 of f is a union of closed sets, well, actually relatively closed sets of closed subsets of 0 1. Therefore, it's a union of closed sets of 0 1, and therefore it's closed. And that's how we prove this relation, right? Continuous curve from A to B and from B to C gives me a continuous curve from A to C. Okay. So this is basically saying, if you want to put it in this more kind of logical language, this is just saying that this relationship of A being connected to B inside of U by a path, right? Being path connected to B inside of U is what we call an equivalence relation, right? So it's reflexive, it's symmetrical, and it's transitive. We're not going to be using much about that, but I mean, it's sort of nice to know. As we're going to see, there's something, at least in the exercises, there's something similar for the concept of topological connectedness, which you're going to see later. Okay, so the rest of the video is just going to be examples of these things. And we're going to start with kind of the two topological spaces that we understand well, or should understand well. So let me first say, I'm just going to say this, I'm not going to write it down, but take any space X with a discrete, that 0, 1 metric that we've been discussing, right? Which is just a source of odd examples, but cares, right? We're odd people, we do math. So in the discrete metric, basically there's no continuous curve connecting any 2 points that are not equal. Therefore, any subset of a space with this discrete metric or the discrete topology, the fine topology, whatever, in such a set, the only connected sets are the empty set, right, where this is satisfied for all points A and B simply because there are no points, or the sets which are singleton, the set that have a single element. If you have 2 elements in the discrete metric, you can never connect them by a continuous curve. Okay, but so that's one example. So let me write here not a proposition that a subset of the real line with the standard topology, so the standard metric, is pathwise connected if and only if it's an interval. And maybe I should remind you of what being an interval is, right? So what does it mean for a set to be an interval? Well, we know, right? So there are half open, half closed, close open, all sorts of intervals. Maybe one endpoint's infinity, the other minus infinity. We have all those sorts of things. But here's a shorter or a kind of more synthetic way of defining what an interval is. And it's this. So take any 3 points in the real line. If x prime and x double prime belong to I, and x prime is between the two, then x double prime belongs to I. So by definition, if you like, subset of the real line is an interval when this happens. There's an equivalent way of saying things which I may use at some point, which is saying a set is an interval if any real number is contained strictly between the infimo of I and the supremo of I is an element of I. So it's saying, okay, I is an interval that contains everything between the inf and the sup, except possibly for the endpoints, right? So that's perhaps even easier to visualize than this. Okay, so we want to prove that pathwise connected sets in the real line are precisely the intervals. How do we prove that? Well, okay, one direction is very easy, which is this direction. What I need to do is okay, here is I, right? I is an interval. So I take 2 points here, A and B, and I need to show that they're connected by a curve. How do I do the curve? Well, I just do gamma of t, say, equal to 1 minus ta plus tb. So that goes from A to B. It's clearly continuous. And because we know that all points between A and B are also part of the interval, we know that the image of this curve is entirely contained in the interval. So that's how you show that points are connected. Just say, okay, if I want to connect A to B, I just go straight from A to B, and then because I know that everything in between belongs to the interval. I mean, here I wrote as if A is less than B, but the same works in the other direction. So yeah, we're good. So okay, a set that's an interval is pathwise connected. Now I'm going to show the converse, and I'm going to show the converse in the following form, right? So if I want to prove that pathwise connected implies interval, I can also prove that a set that's not an interval is not pathwise connected, right? Assume I not interval. So in order to understand what that means, we have to negate this. So I'm going to write it in synthetic form. I'm just going to say there's a point x and another one x prime and another one x double prime. They're listed in order. X and x double prime belong to I, but x prime does not belong to I, right? So a set is not an interval when you have 3 points like this, such that these two belong to I, but this one doesn't. And yeah, so what do we do with this? So let's assume to get a contradiction, right? So we want to prove that non-intervals are not pathwise connected. Assume that nevertheless these 2 points are connected inside I. And what does that mean? That exists gamma 0, 1 to I continuous with gamma 0 equals to x and gamma 1 equal to x double prime. So this is weird, right? So we have a function from 0, 1 to the real line, right? I is a subset of the real line. That goes from x to x double prime. But notice that since I does not contain the point x prime, we have gamma of t not equal to x prime for all t in 0, 1. Right? Again, the image of gamma has to be contained in I. X prime does not belong to I. Therefore, there's no time at which this curve visits point x prime. Why is this a contradiction? Well, we have the intermediate value theorem, right? So we have a continuous function that takes value at 0, takes value x at 0, takes value x double prime at 1. Therefore, any point between x and x double prime has to be in the image of the function, right? The curve has to cross that point at some point, if you forgive me for the pun. Or, yeah. Yeah, so I'm saying, okay, by the intermediate value theorem, if I have these 2 properties, then for any point between x and x double prime, in particular for the point x prime, there must be a t such that gamma of t is equal to x prime. So this is a contradiction because of the intermediate value theorem. Yeah, and that shows us that that this cannot be, right? If I is not an interval, then it's not pathwise connected. In contrapositive form, if phi is pathwise connected, it has to be an interval. And now, yeah, so now we know precisely who the pathwise connected subsets of the real line are. Let me give you an example, or family of examples that it's sort of similar to this one, but not quite, right? So we can see. So now we're going to move to the realm of vector spaces. I'm going to be considering subsets of vector spaces. And when I talk about a vector space, I always assume that there's a norm that I call, the norm of V, such that well, the topology is given by that norm, right? So. Okay, so I'm going to be talking about shapes that are different from this. Well, they're more. Okay, so I should. The proposition is that if C is convex, and I'm going to remind you of what convex is. It's pathwise con. Okay, what is convex, right? So, well, it's convex if for all points A and B inside C, the line segment between these 2 points, and we use this notation for it, which is the set of all convex combinations, right? Combination is this form of A and B. It's contained, so this is a line segment, this is your definition, and C is convex if for all A and B and C, this line segment is entirely contained in the set C. The proposition says that if a set C is convex, then it's pathwise connected, and the reason is pretty obvious. So C is convex. Any 2 points are connected by a curve inside C, and this curve is actually a straight line segment, right? So that you have to check perhaps, but it's really easy. So I'm going to leave it as an exercise. I'm not going to prove this proposition. My main reason for mentioning it is just that, this is a particularly simple class of pathwise connected sets, and convexity is such an important concept that we have to talk about it at a few points in our class. So this is more or less a convex set, meaning that, take any 2 points, the straight line between them is entirely contained in the set. Maybe I screwed things up a little bit over here, but who cares? And here's a non-convex set that's nevertheless pathwise connected, right? Because, well, if I take A and B here, then the line segment between them has points outside Z. Nevertheless, there is a curve that connects the 2 points that's entirely it's entirely inside D. Well, this is convex, and this is not convex. So we're going to be seeing a few things about convexity later in the class, but I mean, that's just one family of examples. So one thing that's nice to check is that, as a matter of fact, all balls are convex. So all balls are pathwise connected, right, in a vector space. And why is that? So take C. I'm going to do it for the closed ball, but the open ball is the same thing. It just changes slightly. So take the ball of radius r around a point C in V, and take A and B belonging to this ball. Then, if I want to argue that if I take T in 0, 1, then this guy, right, this combination of A and B also has to be inside the ball. So how do I do that? I look at 1 minus TA plus TB. I compute the distance of that point to X, so that's just a norm of the difference. And I need to show that that's less than or equal to R, right? So again, in order to show that this point here, this guy belongs to C, to the ball, I need to show that its distance to X is less than or equal to R. And this is kind of mildly interesting. I mean, you have 1 minus TA plus TB. Here you have X. To ease the comparison, I'm just going to say, okay, this is 1 minus TA minus X plus TB minus X. Right? Notice that X here appears with coefficient minus 1. Here I have minus 1 minus T, 1 minus T and T add up to 1. So that's exactly the same thing. But the good thing is that now I can use the triangle inequality. Or sorry, the subadditivity of the norm, right? Which gives me the triangle inequality of the corresponding metric. So here I did 2 steps at once. I'm just going to say the norm of this plus the norm of this is an upper bound. But when I have this guy, I know that the absolute value of a vector, the norm of a vector multiplied by a scalar is the same thing as pulling the scalar outside with an absolute value, but T is between 0 and 1, right? So I'm just saying, okay, the norm of this piece is 1 minus C, the norm of this guy, because 1 minus C is a non-negative real number. The same thing for the other guy, except that I have T. And now watch. So by assumption, A and B belong to the ball. So A minus X is less or equal to R. B minus, A minus, here should be X, right? Here I also have something that's less than R. Therefore, the whole expression is upper bounded by 1 minus T times R plus T times R. But then the T's cancel, right? So this is less or equal to R. So to conclude, what I've shown is that if I have 2 points at the ball of radius R around X, meaning their distance to X is at most R, then the same is true for any point in the line segment connecting A to B. Therefore, this ball is convex. And that's for any norm in any vector space, right? So there's even a theorem that tells you if you have a convex set in a vector space, it's the unit ball for some norm if it's convex, and then you need something else, which maybe I'm going to put in an exercise. at some later point. But in any case, so this is one important family of convex sets. There are many others, right? There are not balls of any norms. Um, and but the point of mentioning this right now is that we have an easy instance of the concept of pathwise connectedness. Okay, I'm gonna finish this video with just a simple exercise that you should try to do. I mean, there are many such exercises, so feel free to come up with your own. And the exercise is this, that if U and U tilde are subsets of X, say it's a topological space, both are pathwise connected, and moreover, the intersection of the two sets is non-empty, then we know that the union is pathwise connected too. And I mean, it's so, I'm just going to tell you how to do it, and you have to check carefully, right? So how do you prove that this is pathwise connected, this union? Well, you have to show that for any two paths, for any 2 points in the union, there's a continuous path connecting the two that doesn't leave the set. Well, if the 2 points are inside U, that's easy, because after all, we know that U is pathwise connected, so there's a path inside U. The same holds if the 2 paths are inside U tilde. What if each one is on one side? So here I have U, here I have U tilde, and they have a non-empty intersection, some point little u inside the middle, and I have A and B that I want to connect. So it should be clear for the picture, right? So all I need to do is take a path that connects A to U, and a path that connects U to B, and I'm done, right? The path from A to U should be inside the set U. The path from U to B should be inside the set U tilde. And I'm done. And I mean, if you want, you can use this fact that we proved that this relation of being connected to is transitive. So there's no big deal. Okay, thank you.